Hello, I'm Aviral. In this talk, I'm going to present a strategy for migrating the R ecosystem to strict evaluation semantics. This work addresses a larger question: how to migrate a language ecosystem. Even a small change to a mainstream language ecosystem is fraught with challenges. If done wrong, it can cause fragmentation of the ecosystem. Users may be unwilling to adopt the changes, and libraries may not get updated for a long time. A language ecosystem can be viewed as an inverted pyramid in terms of usage. Let's take the R ecosystem as an example. The numbers on the side represent the order of developers. At the base, we have the implementation and the order of 100 programmers who intimately understand the internals of R and make commits to the repository. The base packages on top of it have been written for over 2 decades by hundreds to thousands of authors. Next, we have the user packages coming from the official package repository of R, CRAN, which has around 18,000 packages. On top of it are notebooks and data analysis scripts written by users. R Foundation puts the number of users at 20 million. Finally, at the top, we have documentation, books, blog posts, and Stack Overflow discussions. All of this grows each year. At the tip of this pyramid, the implementation level, changes are easier to make. As we move up the hierarchy, the number of people impacted by the change increases. It also becomes harder to communicate the nature of the change we are making to the language. This ripple effect within the ecosystem makes migration a challenging problem. Let's look at the problem of ecosystem migration concretely in the context of R. How can we evolve R, a lazy language, to strict evaluation semantics? Laziness in R is implemented using a data structure called promise. When a function is called, its parameters are bound to promises. A promise contains a reference to the corresponding argument expression, the environment, and a slot in which the result of evaluating the argument is cached. When the parameter is used, the result is computed, stored in the cache, and returned. Laziness is used in R to implement metaprogramming. The substitute function can be used to reflectively access an argument's AST from its promise. In this example, A and B are replaced by the argument text 1 by 2 and 3 into 4 respectively by substitute, and the resulting AST is returned. This AST manipulation enables metaprogramming on function arguments. So why would we want to make R strict? This was investigated in our OOPSLA 19 paper, in which we performed a large-scale evaluation of R codebase to understand the use of laziness. We found that R is weakly lazy. Only arguments are lazily evaluated, return values from functions and assignments are strict, and there are no lazy data structures by default. Most R users don't even realize they are working with a lazy language. The graph at the bottom categorizes function arguments based on evaluation. Always arguments are evaluated across all calls to the function. Never arguments are never evaluated. Sometimes arguments are evaluated only across some code paths. We observe that 87.6% arguments are always forced. They can be made strict. Let's think about how we can do this migration. We can introduce annotations to mark lazy arguments and switch the default evaluation from lazy to strict. Modifying the VM to eagerly evaluate arguments by default is easy, but the annotations have to be inserted manually by the users, which would be error prone. Also, this would be an invasive change for which the authors have no clear incentive. This makes this strategy undesirable. It is unlikely to be adopted for migration. What would be a viable solution to this problem be? We believe a viable solution should have the following tenets. First, we should not require our users to significantly change their code. Second, code changes should be automated, requiring limited manual intervention. Third, the changes should provide direct measurable benefits to incentivize the users to adopt them. Let's look at a strategy for migrating the R ecosystem to strict semantics, which follows these three tenets. Our strategy is to use dynamic analysis to analyze argument usage. For this, we have developed a tool, Laser. Given an R package, Laser runs all the scripts on this package, such as examples and tests. These scripts exercise the package's functions. Laser intercepts these calls and analyzes the arguments to generate strictness signatures for the functions. Laser does not handle I/O. The R ecosystem has a rich collection of libraries for handling data, resulting in a vast API for reading and writing files to disk. Tracking these calls would require tracing syscalls, which is currently not supported by our infrastructure. Laser also does not handle state changes in the native code of packages because there is no particular API that can be intercepted to track those changes. A strictness signature describes the arguments of the function that can be evaluated strictly without breaking code. It starts with the keyword strict, followed by the function name, followed by a comma-separated list of strict argument positions. There is one signature per function and one signature file per package. These signatures can be shared along with the package and read off by the VM to perform strict argument evaluation. Laser automates the process of lazy to strict conversion by generating strictness signatures automatically. This satisfies the first tenet of our migration strategy. Strictness signatures provide a non-invasive mechanism to specify function strictness. This satisfies the second tenet of our migration strategy. Laser's goal is not to infer maximally strict signatures, but to minimize the impact of those signatures on the clients. To understand this point, let's look at how Laser works. On the left, we have a library function M with 5 arguments. On the right, we have 3 client calls to M. Laser says that only argument 0 is evaluated strictly. We will see how Laser tracks the arguments in these calls to infer this signature. When the first call is executed, Laser observes that argument B is not evaluated because A is false. This argument should not be evaluated strictly because it will print one which is not expected. In the second call, Laser observes that argument C is metaprogrammed using substitute. It is not evaluated, so Laser makes it lazy. In the third call, argument D reads R1, which is modified by E. Here, evaluation is order sensitive. In these scenarios, Laser conservatively makes D and E lazy. This gives us the desired strictness signature, strict M0. What happens if we have these new clients instead? We no longer have R3. R1 and R2 have A set to true. In the first call, A is true, so B will be evaluated. Hence, Laser will make B strict. Because E and D are no longer side effecting, they will also be made strict. So, the strictness signature for the same function will be different. If M is now called with R3, it will produce wrong results because it will evaluate D followed by E. This means Laser is unsound. It can produce signatures which can break clients which it has not seen during inference. However, the impact of this unsoundness is limited, as we will see next. To assess the robustness of our signatures, we perform a two-step experiment. First, in the synthesis phase, we synthesize signatures for top 500 packages. This yields signatures for 52,000 functions and 204,000 parameters. Next, to assess their validity, we run 2,000 client packages which call functions from these 500 packages to check if their output changes by applying these signatures. We run the client script 2 times, without signatures and with signatures. Then, we compare the output from the 2 runs. If the output does not match, it means the signatures have affected the result of the script. In this experiment, we found that there were a total of 3,000 failures. Majority of failures originated from 7 packages. Removing those resulted in only 358 failures out of 45,000 programs. So, the signatures Laser generates are quite robust. The impact of unsoundness is limited. However, this unsoundness does imply that signatures generated by Laser have to be manually inspected for correctness before deployment. So we have a tool that aids in removing laziness without modifying code. But what is the incentive for the users to use it? One incentive is predictability. R programmers frequently resort to using the force function to evaluate the arguments in a predictable order at the function boundary. In this example, f takes two arguments a and b, which are forced before being captured by the inner function. If the arguments are side effecting and not forced before capture, it will be unclear when and if the side effects will happen. Laziness is undesirable in this case. There are also bug reports on R's issue tracker arising from the mix of effects and laziness. Thus, predictability is one big incentive for removing laziness. The next incentive for removing laziness from R is performance. While you might expect laziness to improve performance because it delays arguments that are not needed, it actually has a negative impact. Firstly, time is spent on allocating promise objects. Secondly, these promises can contain side-effecting code that obstructs compiler optimizations. We expect strict semantics to improve program performance with a just-in-time compiler that uses advanced optimizations like SURE. SURE is our research JIT compiler. It has two tiers on top of the GNU-R interpreter, a bytecode interpreter and a native compiler which compiles the bytecode using LLVM. Among many other optimizations, SURE speculatively inlines promises and closures. We conducted a limit study experiment on 14 benchmarks to assess the highest achievable performance by moving to strict semantics. We manually picked the strictest, semantically correct signatures for our programs. Only a handful of functions, such as try-catch, had to be kept lazy. Then we compared SURE against SURE-S, that is, SURE with signatures. First, we measure the number of promises allocated by GNU-R, SURE, and SURE-S. The first jump from GNU-R to SURE leads to a 91% reduction in allocations. The second step from SURE to SURE-S leads to two benchmarks not allocating any promises at all, and an additional 96% reduction in the remaining benchmarks. Next, we look at the speedup. As a baseline, SURE already has a 1.89x mean speedup over GNU-R. SURE-S further offers a mean speedup of 1.17x over SURE. 9 out of 14 benchmarks speed up significantly. While some part of the speedup comes from reduced promise allocations, the major speedup comes from not needing to set up the execution context for promise evaluation. This includes marking it as under evaluation to detect recursive evaluation dependencies and calling the interpreter's eval loop on the code of the promise. Having the promises inlined at the call site results in fewer instruction cache misses in the native backend. Part of the speedup is due to better optimizations. Due to strict evaluation of arguments, promises do not leak environments and therefore SURE is able to elide them. So, migrating to strict semantics offers another incentive to users, performance. In this work, we propose and evaluate a strategy for evolving R as an ecosystem to strict semantics. We provide strictness signatures as a non-invasive R extension to avoid changes to legacy code. We automatically infer robust strictness signatures for package code. By turning R into a mostly strict language, we show that SURE runs faster through our benchmarks without any further changes, incentivizing the users to adopt the new semantics. We are currently building upon the success of this work for the actual migration. Thank you.